Okay, this system of three equations is equivalent to having the matrix 1 minus 3, 2, K1 minus 1, 6 minus 5. So that matrix times x, y, z equals minus 7, minus 5, 1. Okay, an alternative way of writing the same thing. We want to know when it doesn't have a unique solution. So it has a unique solution when we can find the inverse of this matrix, and we can't find the inverse when the determinant is 0, because we have 1 over the determinant as part of our inverse function. So we want the determinant of 1 minus 3, 2, K1 minus 1, 6 minus 5, K minus 1 equals 0. So that implies we're going to do 1 times this pairing. So we get 1 times K minus 1, take away 5, so it's K minus 6, plus 3, remember the negative of that, change the sign of that, 3 lots of K squared minus K plus 6. K squared minus K plus 6, and finally plus 2 lots of this determinant, which is minus 5K minus 6. Okay, if we tidy that up a little bit, we'll end up with, we want that to equal 0, so we get 3K squared minus 12K equals 0. So that implies K equals 0 or K equals 4. Okay, for part B, it says, well, what happens if K is 5? Okay, so clearly here we will have an inverse because it's not 0 or 4. So we've got the matrix 1 minus 3, 2, 5, 1 minus 1, 6 minus 5, 4 times x, y, z equals minus 7, minus 5, 1. Okay, and we're going to find the inverse matrix, and in effect put, I'll call it A, the inverse matrix there, and the inverse matrix there, and these two will give the identity, and we'll get x, y, z. Now the inverse matrix we can find on our calculators. So a to the minus 1 is 1/15 times minus 1, 2, 1 okay, and then if we multiply that by 7 minus 7 minus 5, 1, that implies x, y, z will equal that times that, which will give us minus 2/15, 233/15, and 298/15. It actually asks us to solve it, so that's fine. We can put x, y, z, that's perfectly good. Interpret the solution geometrically. Because we got a solution, the three planes meet at a point.